For section 5.4, 5.4 is essentially just the same as 4.9. What is an indefinite integral? Well, essentially, an indefinite integral is just going to be the antiderivative. So, for this case, I really don't want to go over a lot of stuff. I just want to point out some notes, some point that we have to be careful about when we do these kind of thing. Let's just take an example. Evaluate the indefinite integral of 1 over x squared dx. Well, what we can do here is to rewrite 1 over x squared as x to the negative 2 dx, and then we just apply the inverse power rule to find the antiderivative. So we add 1 to the exponent, and then we divide it by the new exponent. And here is the first thing that I want to note. Keep in mind, whenever you take the antiderivative, you have to have a plus c. You have to have a constant because we don't know whether the original function have a constant or not. So first thing I want to note, remember the constant for indefinite integral. 2, remember that these integrals are going to be evaluated from some interval, on some interval. What I mean is that by convention, we really assume that the interval is going to work. For example, in this problem, we cannot evaluate this equation, this function, in any interval that includes 0, because 0 is going to make the function undefined. It's going to make the function discontinuous. And that is pretty much it for the first part of 5.4. It's just finding the antiderivative. Also, please look in your book for a list of common antiderivative that you can use to help you while working through the section. Part 2 of this section is going to be on the net change theorem. The theorem states that the integral of the rate of change is the net change. In other words, note that this theorem is nothing more than the fundamental theorem of calculus part 2. What this is saying is that if you take the integral of a derivative, you just get back the function itself. They cancel out one another. And to take the integral of a derivative over an interval, just take the original function, evaluate it at the endpoint, minus the evaluation at the starting point. For example, let v of t be a velocity function. And the function is t squared minus t minus 6. We want to ask what is the displacement of this object between time equal to 1 and time equal to 4. Here, note that the displacement function is the integral of the velocity function. Another way to state that is, given a displacement function, the derivative of the displacement function is indeed the velocity function. So to find the displacement between time 1 and 4, we are taking the integral from 1 to 4 of the velocity function, which is equal to the integral from 1 to 4 of t squared minus t minus 6 dt, which is going to be equal to 1/3 t cubed minus 1/2 t minus 6t, evaluated from 1 to 4. Plug in everything. 4 minus 1/2 times 4. Oh, sorry, that's a square. Minus 6 times 4. That's the first term evaluated at 4. That's the whole f of b. Minus. Now we evaluate everything at 1. 1 cubed minus 1/2, 1 squared minus 6 times 1. And then from here you can just put everything into your calculator. And the solution would be -9/2. And meters, of course. So that's 5-4. Again, please look in your book for the list of common antiderivative. That is going to be particularly helpful in this section.